show, so the slide's gone. So what we're trying to do is to show that what? F is equal to gradient of m dot b. Okay? This is the force on the magnetic dipole. I told you we'll be using some of the techniques. So, for example, if I take the curl, what are some of the mathematical techniques? Curl of A, the ith component of the curl of A is epsilon, well, I have to sum, I, J, K. So dj a k, for example. And sum is being done on j and k. And in this notation, a1 is ax, a2 is for any vector, ay, and a3 is az. Okay? So when I say sum over j and k, they're going from 1 to 3. And we also surmise that I, j, k, m, n, and you're summing over j. Always sum over repeated index. This is given by what? Delta I m delta k n minus delta I n delta k m. Okay? And then what we have is a coordinate system. And some sort of a current loop. So this is M here, and the current goes this way. The center of the loop is located by R0, and this vector is R. This way is R. So R locates a point on the loop from the center of the dipole, and we can make a Taylor expansion of B around the dipole, because a dipole becomes a pure dipole as the area goes to 0, which means the radius goes to 0. So we can write this as B of R0 plus R minus R0, this is just your Taylor expansion, dot gradient, the whole thing acting on B. You take the gradient acting on B, and this is my notation. So when I didn't want to draw the long line. When I put in R0, I take the gradient and then not the gradient, I take this derivative operator acting on B, and after I take the derivative, then I evaluate it at that point. Of course, if you evaluate it at a point and then take a derivative, you're going to get 0. Yeah? So that is my notation. So now let's write the expression for force. Force is I dl, it's a loop across B, and so I stick this in. I is outside, I can necessarily bring it out, cross, well, let me put this in for the first go round, and that's where we were last time, r minus r0 dot gradient b of r0. Okay. Now, this is a constant vector, so this integral is just dl. So dl is 0 when you go around a closed loop. Same thing over here. This, whatever this quantity is, that's also a constant vector. So the only meaningful term here is I integral dl cross r dot gradient So now what I want to do is change this notation to component by component. Yeah? So what I'm going to do is first, I'm running out of space anyway, so I'm just going to, so this is the status of the problem literally as I left it last time. So it was a little bit of a recall. I'm just going to use these freely. You can see the pattern as I do it, and I should have written it in that corner, but here it is, and it's gone. So we'll pretend as if I've committed it to memory, and I'll execute it. Better still, the notation is so cumbersome that I'm going to consult my notes so that I don't lose indices. Again, this is really for your listening pleasure, but it's good to see it just one time around, as I've mentioned. Okay, so well, I should have erased that, but the ith component, any I, it doesn't matter. There was an I sticking out, well, the current I sticking out, and summation. Gosh, I'm going to write one equation that I'm going to erase. But what did we have? I dl cross r dot gradient acting on, this is what I had, right? So let me explain. I, j, k, this is I, so, and I'm going to sum the three indices. I've not shown you what L is, J, K, and L. When I write this, you should know that it's going from 0 to 3. Okay, let me write out what I have, and I'll explain. This is evaluated at R0. So let me, for the first time around, show you that these are exactly the same. I have brought the I out. Well, I was already out. So look at this. First of all, I have R dot. So if I have any vector A dot B, how can I write that AL, BL? Correct? That's what it is. So you will find I have R, L, and gradient L, summing L. So this is this with the summing of L. Now I have to take the cross product. When I do the cross product, and if I need the ith component, I need to do EI, and then two more indices. And take the first vector and put the jth index, and take the second vector and put the kth index. What's the first vector? DL. So DL, I have the jth index. And what's the second vector? This is a scalar operator. It's this guy. So I have that index. So this translates into that. Now, notice RL, I can write it as R dot unit vector. Do you know what I mean by here? So E1 is X hat, E2 is Y hat, E3 is Z hat. With that notation, I'm writing this as that. Yeah? So, because, see, this is a constant. And I'm going to erase this. I have shown in the last couple of days we used it. Let me write it this way. For a constant vector. Remember, we had shown that. So that means the integral is done freely now. And I'm going to be very careful. Keep this in mind. For lack of space, I'm going to do this. J, K, L. Epsilon I, J, K. This is going to be the area vector crossed EL, but the jth component of that. I'm not going to put an R0, you just know that, well, I can stick that in at the end if you want. Is that just crazy?
You know, integral live in those brackets.
Well, it doesn't, but this is a constant vector. So we can just treat, oh, I didn't even put the integral. I just
That's
put
right.
the, yeah.
And then we got rid of it.
Yeah. There was an integral here, so I forgot to put that integral over here. Yeah? Now, I'm trying to get force, and I need M on the other side, but look at this, I have I times area. So I mean, our hard work is in many ways over. J, K, I have M cross EL, J, now, this is a cross product. Therefore, I'm going to have J, K, L, epsilon I, J, K. This is the jth component of a cross product. So I'm going to write this as epsilon, jth component, m, n. Too bad I used m, because it's very close to n, I used n. And then I have, this is the nth component of the vector m. So smaller font, bigger font. And I need nth component of this one. That's an odd object. That is just delta N L. Of course, I've introduced M and N, so I need correct? I can collapse one of the summation with and this is 0 except when n equals L. So what I'm going to do is I'm going to do two things. First of all, I'm going to have M, N, J, K. I don't want multiple summations. And then I'm just going to write E, I, J, K. Look at this. I have J, M, N, but my formula for summing these had J's in the middle. So I'm going to swap these two. But I get a negative sign. M, J, N. L is gone, so I just get M of N. Look what has happened. M of M. What happened there? Mn. Yeah, so this is, sorry, this is M. This is the, because see, Mn, it's the mth component of M. Now, when N and L is collapsed, L became N.
So the function was operating on the gradient, not on
Yeah, I could either retain N or I could retain L, but I guess I chose N because M is there. Now, and largely because this is exactly the formula that we had. And when we do that, the summation on J goes away. So I have minus, I would have M, N, K, what is it? Delta I M, delta K N. I'll write it as two different terms. M, delta N, dk. The next term is minus, so it kills with that. I would get plus M, N, K, delta I, N, delta K, M, delta N, dk. Are you happy with this? Here I'm using that summation formula. I get two terms. The first one is positive, the second one is negative, but there was a negative sign, so the first term became positive. Negative, and the second term became positive. Okay. Now I'm just going to simplify these two terms, and I'm trying to get rid of summation as much as I can. I'm going to keep K and kill these two. So I would have, make sure this is correct, Mi delta K bk. So what has happened here? K so over here, I replaced N with K. And over here, I replaced M with I. K is being summed. The next term is positive. And again, I get K, MK, delta I, dk. Let's see. N became I.
We're missing an N.
I'm sorry?
We're missing an N in our.
And M is just gone, and it picks out the value K.
But in that one, we just don't have one, right?
There's no M in there.
But we put an N there. On this. kept it
Oh,
at
right,
M.
right. I have, oh, right, M, you're right. M, and that, M became K, sorry. Good catch. Very good. This is, I mean, incidentally, this is Fi. So, what is this guy? This is nothing but, because look, it's being summed. Divergence of B. What's the divergence of B? 0. What is this guy? This is I'm doing a slight cheat because M is a constant vector. I brought it inside the. Now, I want to talk a little bit more about that. And so therefore, I in fact get that. I'll talk about the cheat. But is the steps clear? Okay, so the way we did it, it's a simple loop. And then we computed the force. In that case, M is just a constant. If we did it with a volume current, it's just that we're not doing any problems like that with a volume current. And if we did the same kind of calculations, there the M would appear inside. In our case, M is just a constant vector, so you just pull it out. Yes? Hey, James, come on by. Feel free to drop by my office. Yeah, so I must say, I should really say, how do I write this? Yeah, that's really what this is. See, M, right? But then I'm saying this, taking it in, since M is a constant. So you might say, well, if it's not a constant, it should still belong here. But that's not how the whole argument went. This is more general. Is more general. For example, the argument is very similar. See the classic textbook by J.D. Jackson on electrodynamics. This is the graduate textbook for. We can do it outside of class if we need to. It's not that much more complicated, but this follows from the arguments we have made.
The reason why that term is the divergence is the indices, well, they agree for all three indices, versus here you're isolating an I and then summing it over the three B's.
Oh, so yeah, here it is, A dot B is written as, see? I think I mentioned this before. For any vector, A dot B is sum over, I don't care what index you use, AI, BI. Delta partial x, BX, partial y, BY, partial z, BZ. That is divergence. Here, it is true. It is M dot B, but there's this guy sticking in the middle.
That
Yeah.
would be whatever
Whatever the component is. It's really this, but we're bringing in the M with a little more caution in the argument. Maybe I'll even set it up for you and throw it in the exam. I mean, I wouldn't say blindly, just prove it. I'll set it up and it should follow very quickly. Okay? So what did we do so far? We computed the torque and the force. What was the torque? The curve?
M cross B.
Sorry, not curve, cross product, M cross B. I have a couple of example problems, homework problems assigned, and it's fairly straightforward, so I'm not going to do that. But I want to get into magnetic materials. So these are, and then we'll specialize to linear magnetic materials. I'm not suggesting that these are two-dimensional. Let's just look at a bread loaf of magnetic material. So you can think of this object either by some external means, by inducing a magnetic field, or by some inherent properties that it has, like a magnet, for example. And that is where they're made up of all sorts of, there's no monopole term, dipole, quadrupole, and so on and so forth. But what will we do with the analogy with linear dielectrics or even dielectrics? We'll hang on to the first non-zero term, which is the dipole term. So you can imagine if they're truly magnetic, they have these current loops that is far from what is perhaps going on, but just aligned so that the magnetic moment of each of these guys are aligned. If they're not aligned, you put an external magnetic field and they'll be torqued and aligned. Right? This is how you can make iron magnetic, for example. You just this is how an electromagnet would work. Okay? So the pure magnetic dipole goes into, just like the electric dipole, a magnetization per unit volume. Magnetic moment per unit volume. Like an average magnetic moment per unit volume. We had the expression that A equals mu0 over 4 pi m cross, and I should tell you what is it that we're trying to do. We're trying to get the A field when you have chunks of these. And why? Because if you get the A field, you can get the B field. We had a similar analogy. So what I'm looking for is when you have a magnetic material, what creates the, what are the sources of the A field? Let me recall this comparison. You had a sigma bound and a rho bound, right? And that was, if you recall, I think P dot N, and forgotten, so let me, there it is, divergence of P. So if M is given to you, you could find the surface charge density and the volume charge density of these bound dipoles, electric dipoles. And using the old potential formula, you could just find the electric potential or the electric field. So what we want to do is from here, just do vector calculus till things look like they have been created by some, not surface charge and volume charge, but surface current and volume current. Yeah? Current is to magnetic field what charges are to electric field. Okay? So first of all, this addition changes A. This is not equal to, but it leads to this is where all the sources are. See, M is being replaced by this, but this is magnetization per unit volume, so you have to integrate over the entire volume. In the case of electrostatics, it was 1 over R, it's 1 over R squared here for now. That is because this is, it has a dipole. There's no monopole third. From here, whatever it is we're about to do, it's going to look like electrostatics, but the curl cross product version of it, here it's divergence. What can you expect for volume current to be? Curl of M. You know, and so as we make these analogies, everything in electrostatics is dot product. In magnetostatics, it is cross product. That's all. Before I begin, I want you to remember a couple of equations. This is the expression we're going to start with. Note we've done this, you've seen this a million times before. Why do I need this? Look. Yep. And I think we need one more equation. Curl, this is property F times a vector field A. So let me look at the number. This is property number 7. This is F times curl of A. And I'm going to write this, I mean, this is just, you can easily verify it component by component. And I'm going to write this, and I'm going to say, and you're going to tell me, why did I mean, again, there's nothing insightful here. It is just a straightforward crank. But why did I pause to say, But by the way, we'll need these two equations in what we're about to do. But why that puzzle? What would one need to say? Make that noise. Something that is peculiar to curl as opposed to dot product. Listen, whatever this is like the product formula, correct? Except when you do this on this, there's a negative sign. That is very peculiar and characteristic of the cross product. A cross B is minus B cross A. Huh? Otherwise, you would want the good old Leibniz form, the product formula. It's derivative of F times G plus g times the derivative of f. It's plus. This is a minus because the curl is, it catches the universe in a different way. Change the order and everything, as if order matters. Okay, so I'm just going to use this. There's nothing more here, and just use vector calculus. So, A equals mu 0 over 4 pi. And who likes minus signs? I know I don't, but there's a minus sign here. So I just choose not to write it. And I'll show you why. In the way I write it, it should be clear. Watch it. There should be a minus sign, right? Yeah, so are we good now? Because when you change the from xyz to x prime y prime z prime, this quantity, any function of separation vector, creates a minus sign. Are we good? Okay. Huh? Oh, no, we.
I remember that, but I don't remember why.
Well, what is that? It's 2x minus x prime. What is, treat x as a constant and x prime as the variable. And what's good for x is good for y and z. So for every term, the negative comes out. Nothing miraculous or profound. Now, when I write this equation, and when I have written this equation as property 7, and I've taken the effort to point it out, it can mean only one thing. We use that formula. So we get two terms. What's the, so this is the term, right? Look. This is equal to this minus that. So the first term will be the curl with prime coordinates minus that, which is curl of forgot another vector from problem. We've done this in class at 1.61, 1.62, whatever that is. 1.61 part B. I need a result, and the result is the following. Curl of any vector A d tau is equal to, over a certain volume, it's equal to the boundary, the surface boundary of a cross dA. I think we actually showed this. There's like one category of problems that I did towards the end that was not very inspiring or necessary at the moment, but I said, this set of problem, you will, and I made a point of it, and I said, you will see it in chapter 5. So this looks a lot like that. Now remember, I can write this as correct? Because area vector is the normal to the boundary that we're considering. And when I say normal, I'm glad I didn't erase it. This would be my normal if I'm on this surface over here. Yeah? The outer boundary. Therefore, just in time, picture goes away. I like my first expression. It is curl cross M R prime over R. This is a nice 1 over R potential. Ooh. Minus. I forgot to. When in doubt, check problem 1.61. You'll find that there is a minus taking in there. And then you will get the term M of R prime cross N dA prime for us. This is a vector identity. It didn't make a difference whether we had prime or not. But for us, we're integrating over sources. And then we can define a bound current volume, because this is volume. I define it by curl of M and a bound surface current by M cross N. This is literally like a Coulomb's law. So we have a J R prime, this is sources, d tau prime over plus these are bound, meaning not free currents. These are due to the magnetization, and then I would have K. Yep. And this is the expression I need. Yes.
What did the prime on our operator go with?
Oh, this is for any variable. I mean, yeah. So if I want to locate,
In the one above that.
it doesn't.
Okay.
Good catch.
So this J bound and K bound, for charges it was kind of like intuitive, bound charges and free charges. Is this
Yeah.
just out of analogy?
No.
Or-
Well, sure. We will physically interpret exactly just like we did the divergence of P and P dot N. We're going to do that. But even there, how did we do it? We first got the result by vector calculus, and then we tried to bring meaning to it. So here is the explanation by vector calculus. then we'll talk about the interpretation. Very good. I don't have enough time today to do a meaningful example. So what I'll do is, in the next class, talk about exactly the physical meaning and an application of this to a simple problem. You would think that there's a simple explanation for magnetism, like a ferromagnet, like a permanent magnet. There's not. So we'll skip through that. There's a lot of quantum mechanics going on.